Let's move on to talk about vectors. A vector is an object with direction and magnitude. There's one exception, which is the zero vector, which is denoted as a 0 with a little hat on it. This has magnitude of 0, and you don't need to specify the direction because it has a magnitude of 0. So let's look at what vectors are. Suppose a particle is moving from point A to point B in a straight line, or right here, A and point B. The displacement vector, AB, can be visualized as an arrow from A to B, with this being the tail and this being the tip. If the points have coordinates that we've talked about, like A was A1, A2, A3, and B was B1, B2, B3, then you could express the vector AB as B minus A. And we usually use these sharper brackets to denote a vector. So you'd have, by points, B1 minus A1, B2 minus A2, and B3 minus A3, which this should be a little hat right here. And this would work for R2 as well, but we're just talking about this right now as if it was in R3. So let's talk about some operations with these vectors. So first thing that you'd always want to do with a vector is do addition. So we have vector addition. And the idea behind this is you place the tail of a vector v on the tip of a vector u. And then u plus v would be the new vector where with the tail starting at the first vector and the tip starting at the end of the second vector. So let's visualize this. We have a u here and a v here. And how we would add them together, we would move this tail to this tip. And then the new vector would be the one connecting this tail to this tip. So this would be the vector u plus v, like that. We can think of this as the triangle law, because we look like a triangle here. But a good thing about this is, let's say we started with v instead, right, like that, and then we put u here. Either way we place tip to tail, we're going to get to the same point. And we call this the parallelogram law. So algebraically, what this means is if u is equal to u1, u2, and v is equal to v1, v2, then u plus v is going to equal u1 plus v1, u2 plus v2. So that's addition. What's another thing that we want to do? Scalar multiplication is a good idea. So if we have a scalar c, and we have this vector v, and we want to double its size, right? Then we'd have another vector v. We would want 2 v hat. This should be, just by kind of how we think of scalar multiplication, this is 2 v's, like that, and it's just the same thing as the addition of placing tail and tip together. Algebraically, what this means is if c is in R, and v is, once again, v1, v2, then c v hat is just going to be cv1, cv2. And that's what you have for scalar multiplication. Similarly, what you can think of when you have scalar multiplication is what happens if c is -1. Then you have the negative of that vector. And that is still a perfectly valid vector. It just would turn things in the opposite direction. So if you had this v hat and you multiply everything by -1, then this would be negative v hat. In the same sort of way, negative v hat should just be negative v1, negative v2. Vector subtraction is just putting these two things together. You have your v and your u, and if you do v minus u, then you're just going to, component-wise, have to do v minus u in each component. It's very simple from combining, once you have vector addition and scalar multiplication, to understand how to do vector subtraction.